Hello, everybody. This is the second AMA of the participants from the Cosmology from Home 2021 conference, which is an online conference running at the moment for 2 weeks. We're all cosmologists, which means that we're as expert as you get as a human on properties of the universe as a whole, things like dark matter, dark energy, how galaxies are growing. We also have at least one astrophysicist here who's an expert on stellar evolution. So today we'll be answering questions primarily from a Reddit AMA we did last week. There were too many questions to answer in 1 week, so we're answering more this week, but also on HAPS and YouTube as they come in. So if you're watching this on HAPS and YouTube, please do ask questions, original questions, and even better, follow-up questions to anything that we're talking about. So I'll start, if we can bring up all of the people now, which I've forgotten how to do. This is everyone who's participating, and I'll just ask you to introduce yourselves one by one. So Matthias, can you go first? If you have your mic working.
Yeah, can everyone hear me normally?
Yep, yeah, you might want to get closer to your mic if you can.
I have no idea which mic I am currently at. There's
I see.
the USB mic, and there is the...
Well, I'll start with Daniela then while you're solving that.
Hello, I am Daniela Sade, and I'm a research fellow at the Institute of Cosmology and Gravitation in Portsmouth in the UK. And right now, I'm working at looking at whether the distribution of galaxies in the universe can give us an answer about whether there is an extra fundamental force in addition to the ones that we do know that exist, like gravity and electromagnetism.
Okay, Rachel, do you want to introduce yourself?
Sure. Hi, my name is Rachel Beaton. I'm a postdoc at Princeton University, and my primary area of research is in measuring the Hubble constant, and I do that by studying stars and the properties of stars.
Deanna, do you want to go next?
Sure. Hi, so my name is Deanna Hooper. Some of you on HAPS might already know me. I'm a postdoctoral researcher over at the ULB in Belgium. My work is mainly on the topic of dark matter, which is this weird type of matter that's in the universe that we can't see. My job is to try to figure out how we can study something that we cannot actually see. And I'm here on HAPS frequently because I love doing science outreach. So hello to all of the regulars. Hello to everybody stopping by.
Nico, your turn.
Yes, hello. Thank you, Sean, and everyone for having me. I'm super excited to be back this week again. I am, I said my name is Nico. I work in cosmology at Newcastle University, and I'm able to answer all of your burning questions on cosmology, some general astrophysics, and particle detectors, in particular, the ones that detect dark matter directly. So looking forward to it.
Awesome. And Matthias.
Hello, I'm Matthijs. I have a PhD in general relativity and what happens if you try to quantize that, especially in the context of inflationary cosmology with modifications as scalar tensor theories.
Cool, awesome, right. And I'm Sean Hotchkiss. I am a postdoctoral researcher here in Auckland, and my interests are too varied within cosmology to try and narrow it down. At the moment, I'm working on primordial black holes and trying to parameterize the vacuum energy, distribution of vacuum energy in the universe. Ask me what vacuum energy is if you want to. And awesome, cool. So let's get started. I see Deanna has a question that she wants to answer, which is, how do we know or can accurately prove that the speed of light is what we think it is?
Yeah, so I wanted to address this question because there's a fun experiment you can actually do at home to measure the speed of light yourself. And I'm all for hands-on experiment, and this one involves chocolate. So there are a lot of scientific ways we can test the speed of light, but you can do it yourselves at home. So all you need is a chocolate bar and a microwave. So what you want to do is you want to take out the spinning plate of the microwave, and you're going to try to put a plate in so your chocolate bar is resting on something. Put your chocolate bar in the microwave and turn the microwave on at the highest potency, the highest heat that it has. Turn the microwave on until you start to see the chocolate melting. Now, at that point, you turn the microwave off, you take out your chocolate, and because the chocolate is no longer spinning, you're actually going to have two specific troughs, or depending how long your chocolate bar is, 2 or 3 specific areas where the chocolate has melted. Those areas, the distance between those two, you can actually measure. So if the microwave is doing its usual thing of spinning, everything heats up evenly. But if you stop it from spinning, you can heat up these specific spots. The chocolate will melt in these specific spots. So this is basically going to give you the wavelength at which the microwave is operating. You measure the distance between these two melted points, you get the wavelength. And then you turn your microwave around, you look for where it gives you the frequency. Once you have the frequency, which will be expressed in something over seconds, it's usually expressed in hertz, which just means it's something over seconds, 1 over seconds. So you have a frequency that you've read off of your microwave, you have a wavelength that you've measured from your chocolates. Now you want to take half of this wavelength because what you've measured is the distance between two troughs. Sorry, half or double. Now I'm missing that. Anyway, you take the distance between these two with a factor 2. I can't remember in which direction. I'm sure somebody will jump in with that. And then you can calculate the speed of light. The speed of light is a velocity, so it's going to be in meters divided by seconds. So what you do is you take your meters, you multiply it by your frequency, which is 1 over seconds, and the result you will actually pull out is the speed of light. This is something that is fun because then you get to eat the chocolate afterwards as well. And it's an at-home experiment that you can do with just a chocolate bar in a microwave, and you can get out the speed of light. It's a very, very good approximation. And I've tried this and it does work. And if you want to be sure, you can try it 3 or 4 times, take the average, and you'll have the speed of light.
Cool, thank you. I always feel like a bit of a pedant when I say what I'm about to say, but I guess you have to read the frequency off the microwave, so kind of not doing it entirely from first principles, but
that's true. That's true. If you know the frequency of the microwave, yeah, but you still do need some outside information.
I've always kind of wondered whether there's a way to measure that frequency as well, but I haven't yet ever come up with a way, because if you could, then you really would be measuring the speed. But yeah. The frequency is so large that you kind of need to have it measured. But maybe just to follow up on the question itself, I guess we're sure of this because people have been able to measure the frequency in a microwave, and also we can measure the speed of light and from lasers bouncing off mirrors and things, that you can set up a long enough distance that you can actually see that its distance traveled in a certain amount of time is what the speed of light would be. So it isn't something that is so fast that it's impossible to measure. Cool. All right. So the next question will be for Daniela, which will be, I understand that dark matter's presence is inferred rather than observed. What attempts have been made to directly observe the stuff? Actually, Nico might want to have a go at answering this after Daniela as well, given that I think she's actively been involved in the searches.
So Nico, do you want to start or shall I start? Okay. Actually, we've made more than one attempt. The basic principle relies on trying to get the dark matter to interact with something else or to appear and be produced. What does being produced mean? Well, being produced means that you take 2 different ingredients, you make them, particles, for instance, in the accelerator at CERN, you try to smash them against each other. And because physics at a very small scale is really, really fun and really cool, what can happen is that you start from these 2 particles and can end up with a dark matter particle that then falls into something else. It's like if you try to smash a tomato and an orange and somehow an apple pie appear that then disintegrated into wheat flour, eggs, and whatever it's made of. So yeah, the physics at a small scale is quite fun. You can get 2 ingredients, and provided the energy is correct, you can end up making something entirely different. So at CERN, but not just at CERN, in various accelerators, you try to produce this dark matter particle, and you try to see if you succeeded by looking at whether you've been able to measure the so-called decay products of that, which means if you've been able to produce an apple pie by smashing a tomato and an orange together, you want to see whether you are recovering traces of flours, butter, eggs, apples, and whatever it is that makes up your pie. Another way of doing that is by using a giant sifter and trying to screen everything that's not the dark matter, and trying to get the dark matter to interact with your detectors, which are there to see something. And this is, I think, especially where Nico can say quite a lot about it. In this case, one of the best shields we've found for the everything else is the Gran Sasso Mountain in Italy, which is my home country, and it's a beautiful mountain, really, really beautiful mountain. So in that case, the Gran Sasso Mountain is really high, more than 3,000 meters, I think. I hope I'm not wrong. And you are using the entire mountain as a shield to the everything else you don't want. So then what is left is that which interacts very little with the matter, which is precisely one of the things you expect the dark matter to do. Another thing that would do this are the neutrinos, just in case they come up. For now, I'm just going to be a bad person, mention the neutrinos, let you wonder what they are, and run away. So having this shield for the for the everything else, then we try to wait for a sufficiently long time that we hope one of these dark matter particles interacts with the detector and then try to see the signal we have. Unfortunately, up to now, we haven't been able. This is not necessarily surprising because you're trying to look for something that doesn't interact. It's like you're trying to speak to a loner. You're trying to speak to someone who hates people and never leaves the house and tries to pretend it's not there when they are in the house. So it's not necessarily surprising. And the other thing is that you still have to make some choices about where to look. And because you're trying to find something that you don't know, this is not exactly the easiest thing. And the neutrinos, indeed, which is another particle, that thing that I'm not really going to tell you what it is just to make you hungry, it took, I think, more than 60 years from when it was first theoreticized and measured. And with this, I'm going to leave it to Diana and Nico, who are really working on this.
Cool. Yeah, Nico, you've actually worked on one of these detectors.
Actually,
on the actual
I have
observational
worked on
side.
the one. Yes, I have worked on the one that you were referring to under the mountain in Italy. So just to, I think this is a very good question. So yes, we are there. We, as a scientific community, we are trying to find it directly. So there are three ways that you can find it. It's either in the accelerators, directly from some measurements in astrophysical measurements, or in a detector. Like a particle detector. Now, when I said, for example, in CERN, what they're trying to see if there is a signature during the particle acceleration. So now when I mention signature, so basically you have a model, theoretical model that explains this dark matter particle. And according to this model, you would have a certain signature that you would see. So that means that, for example, we should see the signal of dark matter in a certain energy range, or at exactly a certain energy. And that's how you build the whole experimental setup around this model. And then you try to make your experiment as sensitive and the best as possible, and then you measure. And after that, you analyze your data, and then you see if you found the signature. So this is how it's done. So definitely there are efforts to do that. In this particular case, Daniela already mentioned that, for example, these detectors are trying to directly detect WIMPs. There is Xenon experiment in Italy. There is a LuxSat experiment in the United States, or is it in North America? And then there is PandaX. So these three experiments are very similar to each other, but they're in different parts of the planet. So whoever gets to see the WIMP signature wins, I guess. But there are other things that come out of that. It's not just the dark matter. If you look at Xenon's paper from two years ago, I believe, there was a very nice finding that was not really looked for. The detector was not designed for that, but you can see other things in the detector, like the longest lived isotope so far. So yes, to conclude in short, yes, there are many efforts being done today.
Cool, thanks, Nico. All right, the next question is one that Rachel will have a go at. And is it possible for the dark matter to emit a type of ray to be seen? Will you ever be able to see the dark matter?
Okay, so I'm going to answer this from a slightly specific way that we're trying to look for signatures of dark matter. That's a little different from the way that we just had explained, which was really cool to hear explained. But dark matter doesn't use the electromagnetic force to the best of our understanding, which means it doesn't make light. And almost everything that we know about the universe comes to us pretty much from light, with the exception of things that we've learned from neutrinos and gravitational waves. So you can't observe a photon or a light ray in the normal way that we observe light rays from stars and things like that. However, there's a specific situation that can happen when the density is very high. And when the dark matter density is very high, the likelihood that two dark particles can interact also gets higher. And we go to look at the places where the dark matter nearby is probably at its highest density. We can try to look for what happens when those two particles collide and the matter annihilation signal. To be honest, this isn't something super familiar with, but through the weak force, they can emit a gamma ray. So by looking at gamma ray observations of dwarf galaxies, so these very small galaxies that have very high densities of dark matter in their core, we can look and see if there's an unexplained signal from gamma ray and use that to conduct dark matter, properties of dark matter. So far, no, we haven't seen any strong evidence coming from the cores of these dwarf galaxies, but it continues to place interesting constraints on that likelihood of such an interaction happening, which is a great in the end. And so I study dwarf galaxies a lot, so I always think it's cool something else dwarf galaxies can do. But that's one way we might be able to see a ray coming from the dark matter. And that's a very quotation marks on the ray.
Cool. We have a good question here in HAPS. If you could send a space probe into a black hole, what helpful info, data, etc., could we get before it got destroyed? I'll have a go at that one. So once it's crossed the event horizon, we could get no helpful info, data, etc., before it got destroyed, because nothing will be able to get out of the event horizon. The people in the space probe, or if we were cruel enough to put people in the space probe, they might get some interesting information, but then they wouldn't be able to send it out. But I think if you sent it close to the event horizon and then brought it back out, you would be able to get helpful info. That would be a very, very energy intensive thing, because the closer you get to the event horizon, the more energy you're going to have to expend getting away from it, to the point that if you got right on the edge of the event horizon, it would be an almost infinite amount of energy to get out. Depending on the size of the black hole, it might not be that much information that you would get, because a very, very, very massive black hole, the actual curvature of space-time near the event horizon is not itself all that large. So it wouldn't look all that different to the space probe compared to being very, very far away from it. There are some speculative ideas about how information is gained or lost by black holes that claim that there would be something known as a firewall at the event horizon. So you would be able to test those speculative ideas by getting close to the event horizon and seeing whether anything drastically different happens. But in just normal, ordinary general relativity, you wouldn't actually necessarily see anything that interesting. So you'd be ruling out alternatives to general relativity, I think, but not necessarily seeing anything that interesting. I might just not have enough imagination. There might be one of my other panelists here who's like, Sean, come on, there's super useful stuff. So if anyone can think of anything super useful, jump in, but my imagination is not good enough, it seems.
No, I agree with you here. I don't think we'd really gain much other than wasting a good probe.
Well, I think I agree with you, except I think it's cool to rule out alternatives to general relativity. So yeah, you would be making a strong gravity experiment. So I agree with everything you said, except I like it.
Just now, actually thinking while you guys were talking, I guess there's the accretion disk to a black hole, where a heck of a lot of matter is falling into the black hole. They would have enormously high energy. So coming back to what Rachel was saying about how where there's high dark matter densities, you might start to see gamma rays being produced. If you could get close to the center of a black hole, the accretion disk there'd be a lot of dark matter falling into that black hole, and it would have a very, very large density near the black hole. Now, of course, at the moment, the black holes are so far away that even if they're emitting some gamma rays, we might not be seeing them. But if you could get really, really close, maybe you would. So it wouldn't be the black hole itself that's interesting. It would be all of the other matter falling into the black hole that might then actually be quite interesting. And you'd have super amazing pictures like in Interstellar, but you'd actually have the actual pictures.
Yeah, if it's a black hole that's accreting material from the accretion disk into the black hole, there's all sorts of interesting physics that happens around that accretion disk. Like we think that the magnetic fields in that accretion disk, as they orbit the black hole, they get spun up and the actual field lines and magnetic field kind of get wrapped around. And you can then funnel material through these jets that they form, jets of material. And that's something that people work really hard on some of the biggest supercomputers in the world. And a lot of people at Princeton think about that because it's called a state of matter called plasma, working on jets work. So maybe you don't learn about GR, but we could definitely learn a lot more observing those jets high up, because right now there's no way actually to observe the jets themselves. We just see the material some larger distance away after it's already interacted with the ambient, whatever it runs into. So I was going to say the ambient medium, but just whatever it runs into, we see that interaction, and that's how we make inferences from jets. And you probably learned about GR, but if you don't learn anything super interesting, you learn a lot about accretion disks, which is really where we test how well we understand how baryons work in extreme conditions, which is also really cool.
Cool, awesome. So I think Matthias is having technical difficulties, so we can't go to him for a question now, but we'll go back to Daniela.
Yeah, maybe I'm biased, but I think learning about GR is really, really cool. I don't know what you all have against gravity, but learning about gravity is actually pretty cool. So
yeah, I mean, I guess my point was just that if we believe GR is correct, then verifying that it is correct is maybe not learning anything. But that maybe that's just a semantic point, I guess. Like, yeah, I totally agree with you that doing interesting stuff is interesting.
No, you've offended gravity now.
If I float off my chair into the ceiling, then you all know why. It's been nice knowing you. So yeah, another question for Daniela. I'm trying to imagine holding dark matter, and I can't. Is there a way to shift our thoughts about physics to help visualize dark matter?
Yeah, so I think all of us can say something here. To start with, I think it would be really hard for you to hold dark matter, because given that it doesn't really interact that much with normal matter, it would most likely fall through you. For instance, right now, we're being traversed by, I don't even know how many neutrinos. Nico probably has better numbers about this, but right now we're being traversed by gazillions neutrinos, okay? There's lots of neutrinos that are traversing us right now. Now, today we know that the neutrinos can't be the dark matter, or at least all of the dark matter. In the past, we thought it might be, now we know better. But the neutrinos had several properties in common with the dark matter, including this ability to interact really weakly with everything else. And to give you an idea, in order to stopping them is like so unlikely that it can take one entire year for a huge detector under the South Pole to just detect 10. And I am making up my number. I'm not sure I'm remembering them, but I'm making a reference to the ice cube experiment in Antarctica, but I would need to check those numbers. So unfortunately, I don't think you'd be able to hold it, because it would most likely fall through you.
Cool. Anyone else want to have a go at that? I think, Deanna, yep. I might have something to say unless Deanna also says it.
Yeah, I think obviously I agree with exactly what Daniela said, that you can't really hold dark matter, but there is dark matter passing through you every minute. I had a seminar, or I attended a seminar once by somebody who was talking about dark matter, and he was giving a seminar while holding his tea mug, and he kept making the point, like, I'm not just drinking tea, there is dark matter literally in my mug. This is also true if we consider that dark matter is passing through us every moment, it's everywhere in the universe, then yeah, dark matter is all around you. So you can't directly hold it, because that would be some type of interaction, but you could be surrounded by dark matter, and it's likely that there is dark matter around you now. this led me down a fun question once of could there be like dark matter life forms, and if there were a dark matter life form standing next to you, how would you know? But that's a fun sci-fi question to think about. We don't think, just full disclosure here, we don't think there are dark matter people. To our knowledge, this is not the case, but it's a fun sci-fi thought. But yeah, even though you can't physically hold dark matter, if you hold out your hand, dark matter is there. So I like to think about it like that too.
Cool. Okay. My thought that I wanted to add is that we simulate dark matter quite a lot as cosmologists, where we just take a big box, we put lots of dark matter in it, and we simulate how it evolves in time. And so even though in the real universe we can't see dark matter, we don't know, well, we kind of can infer where it is by how it lenses light, but we don't know what it is, where it is by just looking. We can predict where it is from these simulations. And once you've got a simulation, you're God, right? Like there's no, oh, I can't see the dark matter. You just make it emit some light. You ray trace that light to an observer and you see exactly what it looks like. And so I'm going to share a link in the comments in a second that has a camera flying through a simulation where you see all of the blobs of dark matter all over the place. It also has some, freaky music playing in the background to create atmosphere. Maybe watch it after the live stream, but that is a way of kind of visualizing what dark matter in the universe would actually look like if it did emit light, even though it doesn't emit light. So I'll do that link in a second, but in the meantime, let's see who's next on our list of people. Deanna, I guess you've just answered a question. I don't see any questions from you, Nico, that you're keen to answer. So I'll go back to Deanna and then we can go to Nico after that. So how do we know that the cosmic microwave background radiation is actually what we think it is and not just random noise we picked up? No surprises that Deanna wants to answer that one.
Yeah, it's a CMB question. How can I refuse? So the cool thing is that the CMB was predicted theoretically. It was part of the Big Bang prediction. Like based on our understanding of the universe, we expect there to be this background radiation in the microwave frequency in every direction we look in the sky. But its discovery was actually accidental. Penzias and Wilson they had a big telescope, they were trying to observe things, and they kept getting this background noise, and they actually thought their telescope was dirty, so they went out to try to clean off all of the bird poo, and then they still found this signal, and then they spoke to the theorists, and the theorists were like, yeah, actually, this is what we expect it to be. So we're throwing around CMB just so everybody knows what the CMB is, and of course this had to happen. The CMB is the cosmic microwave background radiation. It is the oldest light we can see in the universe in any direction we look, and we have amazing, amazing maps of the CMB, like the one you can see on screen, which I'm at this point just going to throw into every broadcast anytime I can. It's just a thing that happens. So how do we actually know that what we measure is the CMB? Well, it's the thing, right? If you predict something, imagine you know of an animal that has two legs, it has webbed feet, has wings, it has a beak, it lives in water, quacks. You're going to say, okay, this sounds like it should be a duck. Then if you see an animal that does exactly all of this, you're not going to be wrong if you say that's a duck. So we predicted what the CMB should look like. We had a list of properties, characteristics that we expected the CMB to have. And then we measured something that had all of these properties. So the chances of this being something else entirely that is not exactly what we predicted is very, very low. Every prediction we've made about the CMB has come true. We have this amazingly pretty map, and we can use the CMB for so many things. In one sense, the noise within the CMB is random because it comes from these random quantum fluctuations in the early universe. So there is randomness to it. And it is a background noise, but it is definitely the background noise that we expected because it fits all of the properties we expected the CMB to fit.
Cool. Thank you. All right. Next question for Nico. Probably a very silly question. To the anonymous Redditor who asked that question, a lot of the time the questions you think are silly are actually some of the more interesting ones. When you look at a star or galaxy that's billions or even millions of light years away, how do we know we're not just looking at a memory of our own galaxy of the sun? So I guess they mean our own sun or our own galaxy. Nico, yeah. Do you want to go?
Yes, I agree with Sean. Absolutely not a silly question. So I would also share first of all, I will share with you a link to an astronomically correct Twinkle, Twinkle Little Star. And in that song, in the astronomically correct version, there is a line that says, Twinkle, twinkle, little star, you are small because you are far. So usually the things that are very far away are smaller. And we know that when we look at the sun and during the day, it's pretty big in the sky. So that is the first indication. The second one is that we can now observe it with a very high resolution with many satellites or astronomical probes that are designed to do that. So, and we can calculate actually how far away the sun is from the Earth, and that is 8 minutes. So we are actually looking at the sun in the past, but only 8 minutes, how it looked 8 minutes before. And now I will share, I hope that answers your question, and I will share the link to the Twinkle Twinkle Little Star, but the astronomically correct one. Thank you.
I might have a go at following up on that myself. So there are some speculative theories about the shape of the universe that would mean that distant stars are like, we're seeing distant stars more than once when we look in the night sky. If the universe was topologically closed in the sense that if you go far enough in one direction, you sort of come back in from the other direction, a bit like the sort of stuff you might see in a Doctor Who episode. In principle, theoretically, that's a valid geometry for the universe, or topology. I think mathematicians are probably going to start attacking me. Topology for the universe, but observationally, you can check for that, right? You can look to see if certain patterns repeat themselves. You can see that the CMB is a certain distance away, so that kind of sets some sort of, no, that's not true. That doesn't set a minimum, because the CMB could also repeat itself, but it doesn't. So that does set a minimum size for this repeating. So therefore, because that minimum size is sufficiently large, we can't see our sun again, because if the universe does repeat itself that way, it would be repeating itself further away than we've yet seen. So in principle, in the future, maybe that would have been possible, but we've checked and it didn't happen. I hope that is somewhat intelligible. Who's next? Let's see. Daniela, you haven't answered for a while, so let's see. Do we have sufficiently accurate detectors on Earth to be sure that gravity is not variable in some currently unknown way to fix the dark matter problem? I see. Yes, good question.
Yeah, that's a very fascinating question as well. We have great detectors on Earth, but also on the solar system, and they make some pretty cool constraints to gravity and what it can do and can't do, including some helpful constraints to what it comes to the dark matter. So among the things that you can do is looking at stuff that falls. And one Nobel Prize was given, I think, for work done in 1991, if I remember. So one of the latest of these experiments was an atom interferometry experiment where they were looking at atoms that were falling. And for various reasons, this allowed you to make very precise measurements of gravity, of the way in which these atoms were falling. And it turned out that it didn't look like anything else that's not the gravity we know was there. You can use this. How is this useful for the dark matter? Well, there are some models of dark matter, there were especially in the past, where you had some extra particles that in technical language are called scalar particles. And it turns out that if you have some of those, you would see an extra fundamental force. Well, all the experiments on Earth and in the solar system so far have excluded the presence of such an extra fundamental force. So already this has informed us about what can and can't happen with these models of dark matter, but even more of dark energy, because these were also useful models for dark energy. So the answer is, do we have sufficiently precise detectors? We are fortunate to have amazing detectors. What is on Earth tends to be very precise because we can benefit from the latest technology. Sending something into space is much more difficult because by the time the mission is approved and sent into space and starts the observation, several years have passed. So typically you don't have the latest technology in space. And also by the time it reaches the fringe of the solar system, which has just happened for, depending on how you count it, for 1 or 2 probes, well, that takes even longer. But as far as the Earth and the near solar system go, we have some pretty amazing detectors. One of the coolest that I want to mention is the Lunar Laser Range. So they have put some mirrors onto the surface of the moon, the astronauts have, and we can fire lasers at them, and they hit these mirrors and reflect back. And this allows you to measure the distance between the Earth and the moon to crazy precision. I think to the diameter of one piece of hair, I think, the distance from the Earth to the moon. This is also very helpful in constraining gravity and therefore anything else we may not know. So the answer is yes, we do have some pretty amazing detectors, and definitely we've used them to the best we could, and hopefully we'll keep having good ideas to see what this could entail, not just for the dark matter, but also dark energy.
Cool. I might just try and add some thoughts of my own on that. In terms of modifying gravity to deal with the dark matter problem, there are actually cosmologists who are doing that. They're working on that. So Danielle is right. In the solar system, we have incredibly tight constraints on general relativity. And in fact, on the largest distance scales, the size of the observable universe, we kind of do as well via the cosmic microwave background. But there is an intermediate scale on the kind of galactic scale where there is a bit of freedom to tinker with gravity. And one of the more popular ways to tinker with it comes under the name of modification of Newtonian dynamics, or MOND, or Milgromian dynamics, named after the guy who came up with it. And they do have interesting results there, where some of the stuff that we need dark matter for can be explained by modifications of gravity. One of the problems with that is that on the CMB scales, we absolutely categorically do need dark matter. I think every cosmologist is in agreement on that. So the question then becomes, where does the dark matter go inside the galaxy if the stuff it's meant to be doing is now being done by modification of gravity? And I think there, it depends on one's perspective. I think it's still useful to think about potential effects of modified gravity inside galaxies as being partially responsible for the dark matter stuff, because there are some ways that it does a better job than dark matter on those distance scales. But inside galaxies is notoriously difficult to actually narrow down everything you're trying to predict. So the fact that modifications of gravity do slightly better in some scenarios isn't absolutely conclusive, because it's messy there. You've got all sorts of explosions from supernovae and colliding neutron stars and all sorts of stuff. So one of the answers to that question is that yes, people actually do work on that, and it might turn out that in some way it's correct, but it's not going to fix the CMB dark matter requirement, and it's not going to change gravity, and as Daniela said, on solar system scales. I think, unless someone else has a thought on this particular question, the next question was going to go to Nico. Anyone else on this one? Guess it's no. Okay, so Nico, this is another good question actually. How much overlap does the cosmic microwave background have with my microwave in my kitchen? Are they similar only in name?
That's a very cool question. Whoever asked that, kudos. So yes, the point is that when we're talking about anything scientific, in that sense, you need to talk about the source. So the source of the microwaves in the CMB, now we need a map definitely during this. Thank you very much. So the source of the microwaves in this particular case is different from the source of your microwave oven. Your microwave oven probably has this RF source that was, correct me if I'm wrong, maybe people know, I think it was developed before the World War II by Varian brothers actually, and then I think that Varian now makes high energy machines that are used in medical sciences. So that is the source of your microwaves in your oven. And the source of the microwaves that we observe is cosmic in origin. And well, CMB physicist present, Diana Hooper, can tell more about, and I'm sure that her audience already knows a lot about it. The thing is that this is the frequency of the microwave that we are measuring now is as is because of the expansion of universe. So at the time, it was a different story. But maybe, Diana, do you want to pick up on that to explain better? No. So yes, in short, they overlap only in this frequency range, but the source is completely different.
Yeah, and the local intensity on Earth is different, thankfully. We're not being fried by the CMB. If it had the same intensity as a microwave oven, we'd be in a bit of trouble. Right, so I think next one is Rachel, and this is an interesting one, a bit outside of cosmology, but Rachel's volunteered, so good luck. What's the deal with Mars? Shouldn't we start colonizing the moon? It's much, much closer.
Okay, so the moon is closer, and hopefully this is coming through because my audio wasn't great before. The moon is closer, but the moon is really small. And because the moon has a very low mass, it can't actually keep much of an atmosphere around it. And it turns out because it doesn't have much of an atmosphere, it also doesn't have things like friction that would, say, take little bits on the moon and actually round them out like we have on Earth. And because of that, the space dust on the moon is very sharp. So even if you went and made some sort of dome contraction on the moon, it would constantly be scratched by this very sharp space dust. And so it's kind of hard to figure out how you work your way around that. Also, because it can't hold much of an atmosphere because of its mass, Mars is a better candidate, even though it's further away, because it's more massive and it could hold an atmosphere. And it's going to make it a lot easier to work and build there as well. And also because it has an atmosphere, it's more similar to Earth. So instead of being this, it is a foreign environment, but it's as foreign as the moon is. And so that's one reason folks found Mars. And there's lots of different ways to answer this question, but that's just one thing that I thought of and I thought was pretty neat to share with everyone.
Cool. Well, I'm learning something from this AMA because I did not know that. Right. I think Deanna will be next, and her question is, does dark matter currently interact with matter, or is it something you can only pick up on by studying the imprints of the past on things like CMB?
I swear I did not pick this one because of the CMB. But this is actually something that was one of the main topics of my PhD thesis. So we know that dark matter always interacts via the gravitational force with other particles. So there are four forces that we know of in the universe: the gravitational force, the electromagnetic force, which controls electricity and magnets, the strong nuclear force, which holds atoms together, and the weak nuclear force, which is responsible for radioactive decay. And these are usually, when we talk about particles interacting, it's with one of these four forces. Now, we know for sure that dark matter, both in the past and today, interacts with normal particles via the gravitational force. This is the best way we can try to find dark matter. We can look at its imprints within the CMB, within the structure formation, but all of these are, as you mentioned in the comment, past observables. But there are things we can do today, like trying to directly detect dark matter, where we hope that dark matter has some other type of interaction with normal particles that would make it slightly detectable, just where they could slightly bump off of each other in some way in order that we could actually see them today in our detectors. We haven't found them yet, but we have been able to rule out a lot of things that dark matter could be. So we do know for sure that dark matter, both in the past and today, interacts via the gravitational force. We know for sure that it doesn't interact via the electromagnetic force. We're pretty sure it doesn't interact via the strong force, and we're not so sure about the weak force. It could be interacting via the weak force, it could not be. But during my PhD thesis, I actually asked the question as well of, could there have been other interactions in the past? For an example, could there be a very, very small electric charge to dark matter that would allow it to interact with photons and with electrons? The answer is basically, if so, it would have to be ridiculously small, because else it would have messed up the CMB. So apart from the mention of CMB, I wanted to answer this question because it is actually what I worked on during my PhD. So the short answer is, we know for sure that in the past and today it's interacting gravitationally. The rest we're still working on.
Cool, thank you. All right, Andy asks a very good question in the HAPS comments. What I've never understood is what it means when we say the universe is expanding, because if it's expanding, then what is it expanding into? This is a very intuitive question that makes a lot of sense, but does have an answer. Daniela has volunteered to attempt to give that answer.
Yeah, it's a very good question. I think everybody asks themselves at some point. What it means is that the distances between objects grows with time. So what this really means is that the universe is expanding into itself. Let's make an example. Imagine you've got something elastic, imagine you've got some elastic sheet, let's say, and you keep extending it. Now, because you live in a three-dimensional space, you can see this two-dimensional sheet expanding, and you don't necessarily have problems with it. And if you want, you can imagine the universe being in some kind of higher dimensional space and seeing it expand there, but that will not be especially useful. The point is it's really expanding into itself. It doesn't need something to expand into, because all that this is telling you is that the physical distances between 2 points in the universe is increasing with time. This is what it really means that it's expanding. Then, as far as we can see today, the universe is flat. It means that it's like this giant rubber sheet, which is why I mentioned the rubber sheet and elastic sheet earlier on. And if it's finite, you will see its size increasing or stretching at least. But then imagine it's infinite. Imagine you've got an infinite rubber sheet. Then what will really happen is if you stretch it, it will still be infinite. And if you stretch it even more, it will keep being infinite. And if you do it even more, it will still be infinite no matter what you do. But if you start drawing stars onto this rubber sheet, what will really happen is that the stars you've drawn will go further away from each other. So the distance between these two stars will increase, but the overall object will just have expanded into itself. Then if you like to imagine it, you can imagine it being in some kind of higher dimensional space, but this is not by itself necessary. And just to make it even weirder to you, you can measure the curvature of something from inside that something. Even from staying on the Earth, we can know it's round.
Cool, thank you. I feel like I want to add some thoughts, but I'm worried that because Daniela's answer was very good and complete, I might confuse things, but I'm going to try anyway. I apologize if I confuse things, Andy. But in some sense, the answer to the question is we don't know, right? Because there's an observable universe. Light travels at a finite speed, and we have seen a certain distance away, and everything inside that is, as Daniela said, expanding, moving apart from everything. What it's expanding into is probably, as Daniela said, just more universe. But ultimately, we don't actually know because we can only see a certain distance away, and everything inside that is expanding exactly how Daniela described. For all we know, though, outside of that could be dragons, could be monsters. I don't know. It's almost certainly just more universe, because why would it suddenly stop? But yeah, what's it expanding into? Probably more universe, but ultimately we don't actually know because light travels at a finite speed. The Big Bang happened a finite time ago. We can only see a certain distance away. Nico, did you want to also follow up on that question?
Yes, actually, it was more a comment from Andy. He says, so the universe is as it always was, and it will always be, just everything inside is moving around. Well, depends on how you look at it. If you look at it as a whole, and I'm sure that a lot of astrophysicists would tell you absolutely not true, because everything is evolving. So that's why we have 3 different populations of stars, and galaxies are evolving from one type of galaxy to another. So the answer is exactly the way you look at it, right? So things are definitely evolving in one direction, I would say.
Yeah, absolutely. It's certainly not true that it always was in the past. There was this Big Bang that happened, and go back far enough, there's no galaxies, there's no stars, there's just a hot, dense plasma. And if Katie, who was here last week, was here this week, she'd tell us what's going to happen in the distant future, but she isn't, so we'll have to move on. I think, Nico, you wanted to, and Rachel perhaps as well, answer this quite long question about space debris, which is also an interesting question. So I slowly read it out, and then Nico, you can go first, and Rachel, you can follow up. So how do we know it's not just a lot of rocks or general debris? I guess it must mean dark matter. It to expand. We know our solar system has a sun, which makes up the majority of matter in our system, and then planets, asteroids, etc., and a whole lot of empty space. So the majority of matter is from a bright invisible source. Theory is then that there is a lot of empty space to the next solar system out there with nothing in it. My question is, how do we know that that empty space. It's not really full of a lot of rocks that just haven't coalesced around a star. It's not visible, but it could be a lot more matter than we think is there. Maybe our system is mostly empty space because that matter has coalesced into a star, but not all space is like that. Nico.
Yes, so we know that it's not rocks because we are able to see a lot of rocks and all kinds of stuff, or debris as you call it, in within the solar system and beyond, actually. We might have problems with detecting super tiny rocks around what Mars, or what you call them, near Earth objects, right? So super tiny things that might cause problems if it hits the planet, right? If it's but there are a lot of satellites whose job is to monitor that. But this is peanuts in mass compared to Sun or Jupiter. The other thing that Rachel will definitely is going to be able to tell you, I think, is also that not only that we are able to optically see this, but the way the dark matter is suggested is that you measure the rotational velocity of a system. So of the, for example, planets around the sun, and then if you find some inconsistencies, that will indicate dark matter. And this is how it's exactly done for the galaxy itself. So maybe Rachel, do you want to take over?
Yeah, I was actually going on a slightly different tact, and that is asteroids are hard to see. Some of the stuff is hard to see in the optical because they're actually not making light. They're actually reflecting light or absorbing light. And that's what makes it hard to track asteroids. So your best chance to see asteroids in the solar system, for instance, is when they're at a certain angle from the sun. And then the other thing that makes it difficult to find the asteroids, we're trying to map their trajectories. So you need to observe them several times and map their orbits to a certain precision when they're in near Earth orbits. And so that's what makes it hard. It's not just finding them, it's actually mapping their orbits. But the thing is that asteroids have a temperature. They have a thermal temperature. And even though they're not emitting strongly in the optical, they actually emit a lot in the infrared. And we have a telescope called WISE that's actually just staring off into space all the time. And it observes at temperatures that are very sensitive to small rocks, which I'm going to call dust, and things like that. And we can actually see this stuff pretty well. We also can observe the impact of material between us and stars by tiny changes in the star's spectrum. So that stuff in between us will absorb energy from that star, and we can actually measure it. And even to tiny degrees. And basically, we can't add up. We need 10 times, 100 times more mass sometimes than we see in parts of the galaxy. And if that much mass were in rocks and dust, we would see it. It would be impossible to miss. So one of the projects I work on actually observes in the infrared specifically, and one thing we can do is actually map junk in space. The other thing to keep in mind is that the space in our solar system isn't just empty because stuff coalesced into the star. It's because the planets in the solar system actually do something called clear their orbits. Every time we orbit around the sun, we smack into space junk and it smacks into the Earth. That's how we have meteor showers and shooting stars. So it's not necessarily true that that's why there's not a lot of stuff in our solar system. There's more empty space in our solar system because we've kind of swept it up and collected it over time. And we can actually see disks around other stars. This is a major part of how we think planets form. And it's a pretty big component. And folks study this all the time. Like I know so someone at Princeton actually is sort of like the grandfather of dust. And I mean, he'll tell you if, some of these space debris, we can see it, I guess is the take home stuff. And you just can't account for it any other way.
Cool, thanks. I guess to put things into perspective, there's 5 times as much dark matter as ordinary matter. So that, if we can see it, it's going to be very difficult for all of the dark matter to be rocks. Okay, the next question for Daniela is, are there ways to model the trajectory of a particular galaxy over billions of years? I find that question a bit confusing because we haven't been around for billions of years. We've been around for what, like 100,000 or something, and we have only had telescopes for a couple of hundred. But Daniela, have a go.
Yeah, so what we can do is we can model it, and for a virtual galaxy that is being simulated inside one of our supercomputers, of course we can see what it's doing over simulated billions of years. So of course, they're not going to be actual billions of years because otherwise we would never see the results. But for our simulation of what would happen over billions of years. However, you may say, okay, so that is that one particular galaxy, but what are you really learning from that one? Well, a more interesting answer is that you can also ask statistical questions. So you could start thinking about things like, if I have a galaxy here, how likely am I to find another galaxy 1 parsec away, or 1 megaparsec away, or 100 parsec away? You can start making these statistical questions. So instead of looking at what one particular galaxy does, you can look at what galaxies do on average. It turns out there is a huge amount of physics into this. You can learn lots about the universe by doing this. And in fact, astronomers typically use this kind of information rather, at least cosmologists. Actually, astronomers studying individual objects, they are interested in individual objects, but cosmologists are more often than not concerned about what happens on average to all of these, to these subjects. And typically we look at it statistically. Anyway, if you have a virtual galaxy, yes, you can know everything. As Sean was saying, for an existing galaxy we see in the sky, we can see where it's moving right now. And from that, by simulating its surrounding and everything else we know about it, we can simulate what it's going to do over billions of years. But because we haven't been around billions of years, we can't measure it. We can infer it, though. Anybody else want to add something?
I think that was super satisfying, and I apologize to the Redditor for thinking you said observe it over billions of years. That was silly on my behalf, not yours. Cool. The next question, I think, for Deanna. I don't think the words cosmic microwave background actually appear here. How big was the observable universe before and after the inflation period? I have seen articles that it was smaller than an atom and then inflated to the size of either a grain of sand or a soccer ball. For some reason, this tiny distance had to inflate faster than light. Why would it have to be that fast when light speed for that size difference is already fast?
Yeah, so a lot of tough questions thrown in together there. And I want to start by saying that talking about before inflation is actually something that doesn't really make sense because we can't know anything that happened before inflation. I heard it expressed once in a way that really stuck with me, which was that inflation deletes the memory of anything that came before. So when we talk about time zero, we actually mean after inflation, right? So this is actually leads to a fun debate among scientists as to whether we should count the Big Bang as being before or after inflation. It's basically a semantic issue. But the idea is that before inflation is something that is so inaccessible to us that we can't really discuss it. Now, what we do know is that during inflation, the universe grew exponentially. We're all accustomed to exponential growth. In the last year, we've had to get accustomed to exponential growth of things. So within this time period, the universe grew exponentially. Now, we believe that this inflationary period did not last long. But if this inflationary period had lasted 1 billion years, we wouldn't actually be able to know this. So there was some amount of inflation. We have a lower limit on how much inflation we need to match our predictions, but we don't have an upper limit. There could have been a lot of inflation. But during this period, the universe grew a lot. So it makes it a bit difficult to put an exact size both before and after the end of inflation because we're not completely sure how long inflation lasted. But regarding the question of was this expansion faster than the speed of light? It was. We believe it was. This might come as a surprise to people because we are accustomed to the idea that nothing in the universe can travel faster than light in a vacuum. This is a principle of the universe. It's something we're all very, very used to. But this is really for things moving within the universe. Nothing inside space-time can travel faster than light in a vacuum. But there is no such limit on space-time itself. So it is highly likely that during the time of inflation, the growth rate of the universe was faster than the speed of light. But this does not violate anything because there's no reason why it shouldn't be. And there's also the thing here that when we're talking about a speed, it's always a question of relative to whom, because you can't define an absolute speed. This is something we know from Einstein's general relativity. So when we talk about the speed of expansion of the universe, it doesn't really make so much sense because it's like with respect to who? With respect to the universe itself. It's why we always talk about the expansion rate of the universe in units that are actually not at all a velocity. They are basically distance over distance times second. So every part of the universe of a specific size is expanding at a specific speed. But then you kind of put an observer because you're putting it to a specific size. So I think there were a lot of questions tied together there. So let me just summarize what I said. We don't know what happened before inflation. We have no idea. The universe could have gone faster than the speed of light. That is absolutely allowed and doesn't violate anything. And inflation deletes anything that came before, so we have no idea how long inflation lasted. Not sure if anyone wants to add stuff to that.
Seems everyone's satisfied. I might have there was one question in Reddit that for some reason said question for Sean Hotchkiss, so I feel like I'm morally obliged to answer it at some point. But I think this is something that any of us could have a go at. Is it theoretically possible to determine a ground zero origin point for inflation by tracking the rotation movement of large-scale structures and plotting where everything ultimately started from? Okay, so yes, I guess one could do that. What one would find is that everything inside our observable universe ended up in exactly the same place. And where that place is kind of not a sensible question. I mean, it's a sensible question, but it doesn't have a sensible answer. It would just be at the same place. If from our perspective, everything is moving away. So if we run it backwards in time, it all just comes exactly to where we are. You know, everything in our observable universe will end up where we are. But if you move somewhere else in our observable universe, everything's moving away from there as well. So they would see everything coming back to where they are, which is completely consistent with what we see as well, right? Like us and someone else are moving towards each other, we'll end up at the same place, wherever that place is. We don't know our kind of relative motion in some direction. So yes, galaxies are rotating and they have these sort of velocities that are slightly different to the expansion of the universe. We call that peculiar velocity, as in it's slightly different to the expansion. But the main motion of just about everything in the observable universe is this expansion. It's moving away from us. So yes, one could run everything backwards in time and find out where everything ultimately started from, and that would be all in the exact same bubble somewhere, wherever that is, it doesn't matter. It would just be together. So yeah, it's not like you could point, oh, it's over there. Over there is where inflation happened. It's everything was involved in inflation and it was all together. The whole observable universe was together. I hope that's like a satisfying explanation. And if anyone else wants to add something, feel free. If not, we can go to the next question.
Yeah, can I just add something?
Yeah.
If people can look up cosmological principle, it ties into that. So basically that there is no preferred place in the universe. And because of this cosmological principle, there's a lot of theory and a lot of things are built upon that. And it's based on the observations, actually. So if you look at the large scales, universe on a large scale, there really is no special place in the universe, right? And Diana, maybe you can answer that. Maybe if there was such a place, would it be imprinted in the CMB?
Sorry, can you repeat the question? I was busy answering somebody and didn't.
Yeah, no problem. If there was such a special place in the universe, would it be imprinted in the CMB?
That is a good question. That is a tough question. I would say no. Now, the thing is, every observer within the universe has their own CMB. So the CMB is actually centered around us because it maps the furthest away part in the universe that we can see. And an observer 10,000 light years away would actually see a very different CMB. So we can't really use the CMB itself to see if there's a center, because the answer we're going to get is yes, you are the center, because by construction or by the way the CMB works, it's the light coming towards us. It's actually a fun question that my PhD supervisor would set in exams often, is how far away do you need to go to see a completely different CMB map? And you can actually calculate how many light years away you need to be to have an unrecognizable CMB map. Likewise, how far into the future would you have to be to see a completely different CMB map? So it's a fun question, but I think the CMB doesn't hold the answer to that.
It holds some answers, because I know in the past people were trying to explain away the effects of dark energy by saying we lived in an enormous, gigantic void, that the reason things were starting to accelerate in their expansion is that our local universe is extremely underdense, and that's why, as it kind of emptied out, there was this gravitational effect that the matter around the void was pulling everything out. And in principle, there was no way to sort of falsify that, because you could create just the perfect density profile of matter going away from us being at the center of the void, and you would never be able to rule that out. And of course, you might rule it out by like Occam's razor reasons, that like, why on earth would we be right at the center of this gigantic void? And you really had to be right at the center. But then some people came up with a clever observation via the CMB that, okay, we're at the center, so we would still see an isotropic universe. Every direction should look exactly the same. But anything not in the center of this void wouldn't see an isotropic universe. In one direction, it's much less dense, and in the other direction, it's more dense. And the CMB would scatter off those observers and then scatter towards us. So we would see the effect of that quite large scattering, because they're not seeing an isotropic universe, which would affect how we would see the CMB here, and we didn't see that. It was called the kinetic Synoev-Zeldovich effect, that hot gas in galaxy clusters in these parts of the universe that saw something anisotropic would cause the CMB to scatter, and we would see that scattering. So at the very least, we've ruled out a certain degree of anisotropy of the universe by the fact that the CMB doesn't have this kinetic Synoev-Zeldovich effect in it. But I guess a bit like the non-Gaussianity discussion we had the other day, non-Copernican principle could be non-Copernican in a continuous infinity of different possible ways. So most of them probably aren't ruled outable by the CMB, but this specific one, which I think was quite interesting because it was quite creative, that there were papers being written saying this is completely unfalsifiable, and then someone came along and falsified it using the CMB. Cool. We've had at least one question in HAPS a little while ago from Christian, which was a good one. So if people are going to have a volunteer who wants to answer this, I'll read the question out. Is it possible that there is a flaw explaining in space-time expansion, because space-time is expanding into another universe? I struggled to fully pass that, but does someone else want to have a go at answering that? Daniela, go.
Oh, sorry.
Yep. Oh, sorry. I've put you on screen. Nico, if you want to have a... Daniela, you go first, and then Nico, you can go second. Sorry about that.
Okay. So there is no flaw. There will be no problem. And I don't see any problem with that. The point is we can measure very precisely the way the universe is expanding. So, and it's expanding into itself, by the way. So the point is, this is something we can measure. So I don't see any flaw with that. I am also struggling to parse the question. But yeah, to be clear, the measurements we have of the expansion history of the universe, as we call it, are among the most precise things we have. Nico?
No, actually, I made a mistake. I was not sure. I'm not an early universe cosmologist, so I was just maybe asking my colleagues here, is it has to do something with bubble universes and things like that?
Yeah, bubble universe would be a slightly different thing, though. And by the way, bubble universe is one of the other things that we can actually test with the ever-cool CMB, just in case someone wants to put up a picture of the most beloved CMB again. Yeah, bubble universe would be a slightly different thing. And in that case, there's still nothing wrong. It would rather refer to the fact that during inflation, in the same way that we are creating this particular universe, we can simply create other universes. And then what could happen is that two of these universes may actually collide. And we are fortunate enough that this would leave an imprint in the CMB, and the idea has been tested. So unfortunately, the last time it was done, as far as I'm aware, we're still a bit further away in terms of having good sensitivity for this. But it wasn't found. But I mean, mostly it's because this is a very, very small effect that's not so easy to find. But there is a way to test this, and it's something you can actually do with the CMB. The point is there will be no flaw. There will be no problem with it. So the point is, yes, it may happen, and it's not a problem. There is no flow if it happens.
Cool. While I was talking about anisotropy, Daniela actually mentioned in the private chat that she has made the most general test of the isotropy of the universe. So I'm going to be involved in the Ask Me Anything as a general public member and ask, how do we know that the universe is isotropic? What is the best current measurement of the isotropy of the universe? And put Daniela on the spot there.
Well, it comes from measurements of the polarization of the CMB. So, by the way, Diana maybe later can explain better what the polarization is, because she's really rich. She's made a fantastic lecture, so this is why. Anyway, essentially, what I tested was that the universe expands the same way in all directions. And the way this is done is take some light. So as someone was commenting earlier, I don't remember if it was on the Reddit or here, if light is stretched, then you're stretching the wavelength, it becomes redder, or if you were to compress it, it becomes bluer. Now, if the universe expands in a different way in different directions, then you expect that the light that makes up the CMB will be stretched in different ways depending on the direction it is traveling into. Now, this is the simplest effect. But the other complexity is that there are many ways in which the universe can expand in a different way in different direction, not just by having, for instance, in this direction you expand this fast, and in this other direction you expand in another way. There is actually much more complexity into this, and it's also a very fascinating mathematical subject if you're interested. It's called Bianchi models. The mathematics is super cool. In any case, you will see that the CMB temperature has pretty patterns of spiral, but even more stringently, the polarization we have too. Now, why is this so stringent? Well, there is one type of polarization in the CMB. We call it B-mode polarization. That is really, really small. So small that so far we have measured no primordial B-mode polarization, meaning we have measured no polarization of this kind that comes from the very early universe. We do see some, but it comes from other things. It turns out that if the universe was expanded in different ways in different directions, then you would see a lot more of this. And because you don't, and because the limits are so stringent, you can basically rule out the hypothesis pretty hard. By the way, one of the reasons why we could do this test is because the Planck satellite of the European Space Agency was able to take very good measurements of the polarization for the first time. And so in some sense, it really came at the right moment. Diana, do you feel like saying a bit more about the CMB polarization? I would just say that Diana gave some amazing lecture about the CMB at this conference. Everybody said so. So yeah, I will put in the spotlight just after having complimented you, Diana. Go plenary speaker, please.
How can I refuse after that? Thank you. Yeah, just full disclaimer here that I am running on over a 12-hour day and I am super sleepy, and polarization is a tough topic. But just going to put myself on the screen. So when we measure the CMB, what we're usually measuring is the temperature. So we take not each individual photon, but the idea is we measure the temperature or the energy that each photon has. But there's also information in which direction the photons are moving. So if we consider that the photons move as a wave, they can be coming towards you kind of polarized in one direction, or they can be coming at every possible direction. So I did a broadcast about this where I went into a lot more detail. So I'm just going to keep it brief now and refer to that one where I wasn't so sleepy. But the idea is, if you imagine the photon traveling towards you, there's a direction along which it can vibrate. And we're used to seeing this effect with polarized sunglasses. You might have noticed if you buy polarized sunglasses, when you turn your head, you will see some light differently. And the reason is because then you catch the photons moving at a different angle. Now, if you take a natural light source like the sun, we expect all of the light there to be unpolarized, which means every polarization direction is possible and you get a sum of all of them. But you can also polarize light. There are some specific things like very strong magnetic fields that can polarize light, which forces it to travel along a specific direction. So when we measure the CMB, on the one hand, we can measure these tiny temperature differences, but we can also measure along which direction are the photons moving. And this gives us another huge amount of information about the early universe. And the cool thing is that the results we obtain from the temperature and from the polarization are in perfect agreement with each other. So we can use a temperature one to get the standard cosmological parameters. We can use a polarization one to do the same, and we get exactly the same result from both. And this is a remarkable achievement. There are two different ways of looking at the universe. They contain different information within the CMB, and they are in excellent agreement with our models. So yeah, the nice thing about the CMB polarization is that it's extremely pretty. You can see it here in Sean's profile image. He has a bit of the CMB polarization. If anyone follows me on Twitter, I also have an artistic version of the CMB polarization as my header image, because it is the most pretty map we have. I love the CMB temperature anisotropies, obviously, but the polarization one is super pretty. I hope that was a somewhat acceptable explanation of polarization. Thanks for putting me on the spot there, Daniela.
I guess it's only fair after I'd put her on the spot that she got to put someone else on the spot. There's a nice discussion going on in the chat between Andy and the panelists about the expanding universe. I was thinking I might just add a thought myself. If the universe is about whether there is a center to the universe, if it's expanding, I think if the universe is finite, then by definition there kind of is some center. There's some point that is like most equally distant from everything else. I mean, if it's finite and not like closed in the sense, like as I was talking earlier about topology, where if you go in any direction you come back where you came from. But if it's truly infinite, there doesn't have to be a center, right? And one of the ways that I found quite compelling to understand this when I was a student was think about the integers. There's no center of the integers. You might think 0 is an integer, but there's just as many integers above 0 as below 0. And there's just as many integers above 4 as below 4. There's just as many integers above 100,000 as below 100,000. There's no center to the, although he's just said in the comment that Nico gave a great explanation, so maybe mine is a waste of time, but there's no center to the integers. But if you kept doubling the integers, you'd keep getting each integer further and further and further apart. 1 would become 2, and 2 would become 4, and everything would get further and further apart. So that's kind of what's happening in the universe if it's infinite. And then I'll answer one other question, and then we can go to a wrap-up thing. So another question was, as I understand, matter interacts with gravity to distort space-time. My question is, does space-time also interact with itself? Perhaps out in intergalactic space where the gravitational effect of matter is weak. So yes, gravity does interact with itself and produces gravitational waves because of that. So when two black holes collide, it's sufficiently explosive to gravity that gravitational waves get produced. And then that gravitational wave is able to propagate because gravity is interacting with itself, because it is causing the space-time to contract in one direction, which causes it to then expand in the other, and it just ripples through space. The same way that an electromagnetic wave sort of mixes between being an electric field and a magnetic field and is able to sort of propagate itself through space, gravity does as well. So yes, you can have a vacuum in the sense that there's no matter there and still have space-time curvature that is propagating through space. I mean, you do need the matter to get the wave started, but then it can propagate because it's interacting with itself. If anyone else wants to add a thought about that question, feel free. If not, then we can go to a kind of wrap up. I don't see anyone wanting to do that. Okay, so the wrap up question was, what would you say has been the most rewarding aspect of your research? Does anyone want to volunteer to go first while the rest of us have a quick think? Nico, maybe, do you want to go first?
Yes. When you start in science, I guess everyone wants to discover something, right? But then when I was still in my undergrad, I think I was working as some sort of mentor in a summer school, and I met a person who is #1 in the world who discovered the most small bodies, and I think even 2 comets. His name is Korado Korlevic in Croatia. And I asked him, how does it feel to discover something? He's like, yeah, at first it's really cool, but then like you get used to it, whatever. And he said to me, it's not like discovering something. What I discovered is more rewarding is like if you develop something and other people use it. And then I brushed it off. I even forgot about it. But then later, in my research, I think so far the most rewarding is that I designed something that a lot of scientists are going to use. For now, it is an electric field in the xenon detector, and soon, hopefully, I will make some contribution in the weak cleansing by modeling weak cleansing and intrinsic alignments. So I would say that.
Cool. Who wants to go next? Deanna?
Sure. So I think there are a lot of rewarding experiences and rewarding moments when doing research. I think not so much about discoveries, but for me, it's that moment when you see something that you're the first person to see. Right? And it might not even be something groundbreaking, but you're just the first person ever to do this. During my PhD, I had the task frequently. Most of my PhD was basically here's a model, implement it in the code, see what happens. And sometimes they were models that other people had done, and sometimes they weren't. And then you get to try something and know that you're the first person ever to see that. And that moment, and you want to share it with people, and you call over your colleagues, like, look, and they don't know what you're working on. It's like, you made a plot. It's like, yeah, and we're the first people ever to see this plot. And that feeling, it never gets old. There can be times where that doesn't happen in a while, but when it does, when you get that moment of, I'm the first person to do this. It's just so amazing. It's like you've pushed human knowledge very, very slightly. And even if it turns out to be something meaningless, you were still the first to find that. I think that's one of the things I love the most about being a scientist is those small moments.
Cool. All right. Daniela or Rachel, who wants to go next? Hand up. Neither of you? We'll go.
I can go.
Rachel,
Mine, exactly.
Oh.
You can.
Rachel put her hand
Oh,
up.
I was
so
going to
go
say, I actually, yeah, I was going to say, because I'm an observer, I go to telescopes and I look at patches of sky that no one ever looked before. And I do that a lot, and you kind of do get used to it. And so I think of that bit, at least. Uh-oh. Am I still here? Don't know.
You are.
Yeah. Still here. Still here.
Okay. A big pink blob popped up, and it was very confusing. I really enjoy giving other people the tools to have that same discovery moment. That I find that discovery moment extremely powerful in the same way that Deanna does. But I get a lot more joy about helping people experience that moment on their own, especially when they come in and feel like it's impossible to do X, Y, or Z. And so I kind of have, and maybe it's just because I'm a little more senior or something, but like I've gotten to the point where getting other people to do the great discoveries and facilitating them to do that is the most rewarding thing in the possible to me.
Cool. And then Daniela.
All the times that I had spent a crazy amount of time trying to get something to work, and at some point it did. And what came to my mind was this moment during my PhD when I had worked a month on something that I never thought was going to work, like never. And at some point I was in the office, 22:15, and finally it works. Finally, I'm able to see that it works. And I was so excited. I danced in the office, and because fortunately at that moment there was no one, I can just tell you that if you've got a swivel chair and my Sharona, you can do amazing things in an office. And then I called the pizzeria close to my place, and I asked them if I could have a pizza. They said they were closing down. I could hear the other girl was Italian like me. So I literally told her, look, I've been working on this for months. I thought it would never work. Please, can I have the pizza? And so she understood. She said, oh, yeah, I understand. This is really important. By the way, it's a Franco Manca in Barlam. Thank you for that, if you're listening. Yeah, I went. It was a very special moment. It happened more than once. It's all the times when after, like literally giving it your all, at some point you understand, you figure out what's going on, you make it work. Yeah, I love it. I love that light bulb moment when it works, when you know what's going on. It's special. I don't think it's very different from children play, by the way. If you can remember child play, it's not that different, in my opinion.
Cool, thanks. I guess it leaves it to me. I think it's similar to what a few of the others have said about kind of when understanding something, when it all comes together. I've noticed a lot of the time I've found as a researcher, I've had clashing intuitions. I've had intuition A, which I'm absolutely confident of, and intuition B, which I'm absolutely confident of. And somehow intuition A leads to conclusion A and intuition B leads to conclusion B, but conclusion A and conclusion B are just completely mutually exclusive. And it's like, what the hell? What is wrong with intuition A or intuition B? And then you're just thinking and thinking and thinking and thinking and thinking. and then finally you find like how it all fits together, and it's like working on a jigsaw puzzle, and then you don't see the picture that you're producing, and then at the end you can kind of see, once you finished, this is what it's all been doing. And physics, I think, maybe this is just a bias of knowing my own field better, but physics is one of the fields where it happens a lot, because even as a student, you're learning about things like quantum mechanics and special relativity and general relativity, which is just so counterintuitive. And perhaps people in the audience might be a little bit familiar with special relativity and things like barn door paradoxes, where you're running into a barn with a ladder, and how does it fit inside the barn and things like that. And when you first encounter that, you're like, yeah, okay, this is impossible. Special relativity is broken. Like, these people are crazy. And then gradually, as you learn more special relativity, eventually you're like, oh my God, actually, this is all internally consistent. How the hell does this work? But it does work. And physics is just constantly that. I mean, cosmology, again, is throwing up stuff like that all the time, where you just think things couldn't possibly both be true, and then finally you kind of work out why it does. And then there's just this satisfying growth of understanding of how it's all kind of fitting together, which I really, really like. Cool. Well, unless anyone else has a final take-home message that they want to share with everyone, that will be it from us for today. So tomorrow we will be doing a recap of the whole conference. So that's not an AMA where we're answering questions, but it's where we're talking about what we have found interesting during the conference, which I quite like as a concept, because it gives us a chance to tell you what we think is interesting, rather than just letting you guide the conversation, because some of the stuff that is interesting you don't even know to ask about, and then we can ask. But you can ask follow-up questions during the broadcast. Deanna broadcasts weekly, so if for some reason you don't already know of Deanna, you should follow her, and I think it's on Sunday afternoons that she broadcasts.
It's usually Sunday afternoon. It won't be this Sunday. I'm maxed out on broadcasts.
Sure. I'm probably going to start broadcasting weekly or fortnightly, and probably on a Sunday evening. It will be Monday morning New Zealand time. I don't know about the others, but you should follow them just in case they wish to broadcast. And if you're coming tomorrow, see you tomorrow. If not, then see you in the coming weeks.